Well, hello again. If you're back for the second video, this is a follow-up to the first one where I showed how calculus is used to derive the equation for the electric field associated with a line of charge. And kind of went through that in a bit more detail than I will on this one. That one I showed how you take sort of a non-calculus approach, something that you can imagine doing sort of brute force or by hand. It would take you a long time. And then show you the parallel method using calculus. I think I'm just going to use calculus on this one. So it'll be a little shorter, hopefully. So what we have here is a semicircle of charge. And in other textbooks, for example, my old Halliday and Resnick and Walker, I think ninth edition, they show it's not a semicircle, but it's just part of a semicircle. So you could do this with any part of an arc. And then what we're looking for is the electric field at the very center. It would be a very difficult question if we were to ask the field at any other location. I might get arrested for abuse if I were to ask you to do that. But I think the center provides enough symmetry that, that this doesn't make it too hateful. So the process here is, get a decent sized pen, is to imagine first, like we did before, just a little sliver of this semicircle that's going to be used to find the fieldlet, or the small contribution of the field. So that little segment, I'll imagine, is down here, some distance from that bisector line that I drew there. We'll call that little segment a little ds, because I'm going to call the distance that little segment is from the middle, I'll call that s. Okay, so this little segment, too skinny to even really draw, so I just drew the kind of the thickness of it. We'll call that a ds. What do we know about that ds? Well, it has a little bit of charge on it. The amount of charge, of course, depends on how much charge is put on the line. And so I'll write a relationship over here, just some preliminary things, that if the entire semicircle has q on it, if we take that q and divide it by the entire length of the semicircle, which is half of the circumference, or pi times r, then that gives us an expression for the charge density lambda. Or written a different way, q is lambda times pi times r. How much charge does mine have on it? Well, it's going to depend on the thickness, of course. So what we do is we say that a little bit of charge on there, that's an infinitesimally small amount, we'll call it dq, is just lambda times the thickness of that little sliver of the semicircle, and that's a ds. I called it that a moment ago. So we'll come back to that in a little bit. So we're going to need that to write the expression for how strong the fieldlet is due to that little sliver. We also need to know how far it is, and I think that's pretty easy to describe because we're just going to call that the radius of the semicircle r. One thing different about this semicircle here is that those distances r will not depend on which little sliver of charge you pick, because we're right at the very center of the semicircle. So now I'm going to write the expression for the small little fieldlet, dE, and what I'm representing here is, let me just draw what the field would look like due to that. It's a positive charge, so it would have a field kind of like that. So that's what the little fieldlet dE looks like. But of course, imagine that there's a piece symmetrically above that bisecting line. It's going to create the same amount of field, but down into the right. And so as we found for the line of charge, we're going to have two components that just cancel each other out. So we really only need the x component. So I will draw that and label that dE sub x. And that will just be found from dE times the cosine of that angle theta that it's making. We'll maybe label that over here as well. And so we just really need to sum up those. So our dE can be written as, just like we can for any point charge, kq over r squared. So in our case, it's k. How much charge is that? Well, that's dq. and the distance away is r squared. And to save a little space, let's go ahead and incorporate the cosine of the angle so we can just get the x component. And it came out a little ugly. Rewrite that. Cosine of theta. Move some stuff up out of the way so we're not getting things mixed around here. There we go. So that's what I might refer to as the strength of the little fieldlet that I drew there, that little sliver of charge. So now we're going to make a different kind of substitution. Because we have some circular shape here, I'm actually not going to try to replace the theta like I did with the long line of charge. In fact, it's going to be better to try to replace the dq with something in terms of theta. Okay, now I have to take you back a ways. We haven't really seen this in a while, and so I need to remind you of something important. I think I'll draw a little supplemental figure just to help you with this. When you're looking at part of a little arc like we have here, with a little length ds, that's related to the angle that's inside that little arc. We'll call that a d theta. And the relationship depends on r. This relationship is ds is r times d theta. And so when I do a couple substitutions here, you're going to see that I'm going to get rid of dq very nicely. So I think I think you can follow this. I'm going to replace ds with r d theta up here. Okay, and then I'm going to put that in for dq there. So I'm going to do a lot of things here. Again, just trying to keep this from getting way too long. So my little fieldlet now, its next component, is going to be written as k. And then here's that double substitution. First replacing ds and then replacing dq. It's going to be lambda r d theta. And then everything else is just the same. So I still have my r squared down here. I still have my cosine of theta because of the component. And so now it's starting to look like something that you might be able to solve in a calculus class. Let's clean things up a little bit. First, to clean things up, I think I'm going to get rid of this little fieldlet idea and say, no, what I really need is the entire field created by all the little fieldlets when we sum them together. How do we sum things together in calculus? Well, you write a big summation like that. That's what gets you the entire electric field. Now, in calculus, I hope they've taught you to take anything that's not one of your variables, something that's just a number or a constant, just pull it out of the mess inside the integral, and things start to look a whole lot more manageable. So what would that be? Well, we have a k, we have a lambda. We actually have r's on the top and bottom. Ends up with just a single r on the bottom. And now I can't pull out the cosine of theta because it has the theta in there. So I'm going to go ahead and put my integral sign in. Then I'll put cosine theta. And obviously I still need to have d theta to remind me of what my variable is at this point. But look at that. That just ends up being an integral that you've certainly learned fairly early in your work in integration. So, oh, you know, something I really need to go back up and do. And now that I've got a nice, fairly manageable integral, what are the limits of this? Let's go back up to the figure. Remember our variable now is theta. So it's like how big and how little can this theta that I drew here get? Well, for a semicircle, it can go up 90 degrees, or pi over 2, and it can go down 90 degrees, also called pi over 2. If you had a different size arc, maybe 60 degrees up and 60 degrees down, then you could use those corresponding numbers of radians as well. But I'll just write it here, pi over 2 and negative pi over 2. Okay, now kind of cranking away. Some calculus. The last video I didn't carry through the calculus, but this one is even manageable enough for me. So I have my k lambda over r. I'm going to do my antiderivative of cosine, which I did have to actually look this up to remind myself. That's sine. And then my lower limit, my upper limit, remember, you then subtract those, and k lambda, whoops, getting a little hasty here and making careless handwriting. Can ruin a good math problem. So I need to evaluate the sine of, oh, see, let me do that mistake there. That's a positive limit on top. The sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. So everything we have there in parentheses is just 2. 1 minus a negative 1. And so that's it. In fact, I think I'm just going to write this 2 to save myself from writing anymore, just like that. And that is an expression for the electric field at the center of a semicircle of radius r and of charge density lambda. So I don't know, maybe that one was a little easier than the long line. I'm not sure. Still the same kind of elements in there that I want you to recognize. So there's the second one, and like I said, that's going to be the last video I'll do. So I'll let you look through some of the other ones in your text or other references. See if you can follow along the way you did there. So that'll do it for now. Good luck with the rest of it.